Welcome to the video lecture on sequences. A sequence is defined to be a function whose domain is the set of positive integers. So, for example, you can write a sequence in function notation like f of n equals 1 over n. But here the n, the domain of those n's, is going to be positive integers. So you're only going to let n be 1, 2, 3, 4, 5, and so on. Only positive integers. Another way of representing a sequence is by writing its nth term. So that's what this a sub n is. This is the nth term of the sequence, which has as its formula 1 over n. So the first thing you want to be able to do with a sequence is figure out some of the terms. So let's write the first 6 terms of each of the following sequences. So here's my nth term formula, sine of n pi over 2. So first thing I want to do is figure out what happens when n is 1. So if I plug in 1, I'm going to get sine of 1 pi over 2, or just sine of pi over 2, and we know that that equals to 1. If n is 2, we're going to get 2 pi over 2, which is just pi. So this is sine of pi, and sine of pi is 0. If n is 3, then we're going to get sine of 3 pi over 2, which is negative 1. If n is 4, we're going to get sine of 4 pi over 2, which reduces to 2 pi, and that's back to 0 again. If n is 5, we're going to get sine of 5 pi over 2, which is the same as pi over 2, so that's 1. And if n is 6, we're going to get sine of 6 pi over 2, which reduces to 3 pi. That's the same as pi, and sine of pi is 0. So these are my 6 terms down here. Now the next sequence uses something called factorials. That's this exclamation point. And what that means is that you take the beginning number, this n, and you multiply by every integer less than it all the way down to 1. So n factorial means n times n minus 1 times n minus 2 times n minus 3 all the way down to 3, 2, 1. So for example, 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. So if we start off with n equal to 1, this is going to be 3 times 1 factorial over 1 minus 1, which is 0 factorial. Now 0 factorial is defined to be 1, and 1 factorial is just 1, so 1 times 3 is 3, so this is going to equal 3. If n is 2, we're going to get 3 times 2 factorial over 2 minus 1 factorial, which is 1 factorial. 2 factorial is 2 times 1 or 2, and 2 times 3 is 6, and the bottom is just 1, so this is going to be 6. If n is 3, we're going to get 3 times 3 factorial over 3 minus 1, or 2 factorial. Now 3 factorial is 3 times 2 times 1, which is 6, and 6 times 3 is 18. 2 factorial is 2, so this will be 9. Now you can see that as these numbers get bigger, this is going to get more tedious to do. But what I want you to notice is we can do a little simplifying from the start, which will help make us figure these out a lot easier. Remember that n factorial by definition is n times n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. So n minus 1 factorial is n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. So all of these factors on top will cancel with all of these, meaning the only thing we'll have left is that 3 and that n. And in fact, when n is 1, we get 3. When n is 2, we got 6. When n was 3, we get 9. So if n is 4, we should expect to get 12. When n is 5, 3 times 5 is 15. And when n is 6, 3 times 6 is 18. So by doing a little bit of simplifying first, we can get a much easier route to our answers. Now this next example here is called a recursively defined function. The a sub n plus 1, the nth plus 1 term, depends on knowing the a sub nth term, the term right before it. And they have to tell you where to start with. So they're going to tell us that a sub 1 is equal to 4. So if we want to know a sub 2, then that means we're going to use 1 for the n, so that we get 1 plus 1, which will give me this a sub 2. So if I use n equal to 1, this becomes 1 plus 1 over 2 times a sub 1. So a sub 2 is defined this way. 2 on top over 2 on the bottom reduces to 1, and a sub 1 was 4. So that means a sub 2 is 1 times 4, or 4. Let's try it again for a sub 3. Now to get a sub 3, you're actually using an n of 2, because 2 plus 1 gives you that 3. So we're going to use n equal to 2 over on this right side. So this will be 2 plus 1 over 2 times a sub 2. 2 plus 1 over 2 is 3 halves, and a sub 2 was 4. So if I reduce here, that's going to give me 6. So a sub 3 is 6. So a sub 4 is when we're letting n be 3. So this will be 3 plus 1 over 2 times a sub 3. That's 4 over 2, which is 2. And a sub 3 was 6. So this is 12. A sub 5, we're actually going to use n equal to 4. So this will be 4 plus 1 over 2 times a sub 4. That's going to give me 5 halves times 12. Reducing, 5 times 6 gives me 30. And finally, a sub 6 will let n be 5. So this is 5 plus 1 over 2 times a sub 5. So that's 6 halves, or 3, times a sub 5, which was 30, and 3 times 30 is going to be 90. So there's my a sub 6. So there's my first 6 terms. Okay, on the next example here, we want to write the next 2 apparent terms in the sequence. So we have 7 halves, then 4, then 9 halves, then 5. So if you can see what the pattern would be here, looks like every other one is going to be a fraction. The numerators of the fractions are odd numbers, 7, then 9, so the next odd number would be 11, and that denominator is consistently 2. And then the second and fourth term, those even terms, are just nice integers, so 4, 5, then this would want to be 6. So it looks like we're going to have 11 halves and then a 6. For these 3 problems, we're going to do what we did earlier with those factorials. We're going to use a little bit of reducing to help us figure these out, so we don't actually have to compute 25 factorial, which would be a really huge number. So what you want to notice is that 25 factorial is really 25 times 24 times 23 factorial, 23 on down to 1. And that 23 factorial is going to cancel with the 23 factorial on the bottom, so we really just need to multiply 25 times 24. So this is just going to be 25 times 24, which is 600. Okay, so using this next example in the same way, n plus 2 factorial is going to start at n plus 2 and then go down by 1, which would leave me with n plus 1. Then if I subtract 1 again, that's going to give me an n, and then it would be n minus 1, n minus 2, and so forth. So from n on down is just an n factorial. So the n factorial on down, those cancel. So this is going to be just the first 2 terms multiplied together. If I have 2n plus 2 factorial, think of that as 2n plus 2 to start. Then you're going to subtract 1 from that. So 2n plus 2 minus a 1 is going to be 2n plus 1. And if I subtract 1 again, then that's just a 2n. And from that point on will be 2n factorial, which will cancel with the 1 on the bottom. So this is going to be 2n plus 2 times 2n plus 1. The next thing we want to do with our sequences is be able to write out a formula for the nth term of the sequence. So this first one, we've got 3, then 7, then 11, and then 15. This is called an arithmetic sequence because each term is going up by the same amount. And what's that common difference here? 3 to 7 is a difference of 4. From 7 to 11 is a difference of 4. From 11 to 15 is a difference of 4. So this is called an arithmetic sequence, when you're adding the same amount each time to get the next term. So in order to get a formula for this nth term, it turns out to be this first term that you're starting with plus 1 less than the number of terms you want. I'll write that as n minus 1 times that common difference. So if you think about why this would be the case, to get to 7, I want to start with 3, and 7 is the second term, so I want to go 2 minus 1, or 1 away, times 4. So I want 3 plus 1 4. To get the third term, I want 3 plus 2 4s. To get the fourth term, I want 3 plus 3 4s, and so forth. So if you simplify this, this is going to be 3 plus, when I distribute that 4 across, 4n minus 4, and 3 minus 4 is negative 1 plus 4n. So our nth term here, if I switch the order around just to make it look nicer, is going to be 4n minus 1. And you can plug in 1, plug in 2, plug in 3, and verify that you get each of these terms. How about this next example here? This one has a couple of properties to it. Notice first of all that the terms alternate. We start with a positive, then we go negative, then positive, then negative. Now an easy way to write that alternating sign is to write it as a negative 1 raised to a power. Now this power can either be n, or n plus 1, or n minus 1, and it's going to depend on whether you want the odd or the even terms to be positive or negative. We want the even terms to be negative. So if I let this power be just n, then if n is 1, then that very first term should be negative, and that's not what I want. So if I add 1 to this, then when n is 1, this will actually be a square here, so that first term will become positive. And then when n is 2, 2 plus 1 is 3, that's odd, so now the second term will become negative. So by adjusting that power, you can make it so that your even or your odd terms are positive or negative, however you need them to be. Now let's look at the actual numbers themselves. What you should notice is that 4 is a nice perfect square, 2 squared. 9 is 3 squared, 16 is 4 squared, and so forth. So these are acting like 1 over your n squared, because 1 is like 1 over 1 squared. These are fractions, so you want a 1 on the top, and you want that n squared on the bottom. So the second term had the 2 squared, the third term had the 3 squared, the fourth term had the 4 squared. So this number here should match the number of our term that we want, so that's our n. So here's our formula for our nth term. The next one, we've got 1 plus a half, 1 plus 3/4, 1 plus 7/8, 1 plus 15/16. So they all start with a 1 plus, and what's changing are these fractions here, 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 and here. So what we need to figure out is some kind of a pattern. What I notice in the bottom is that I've got 2 to the first here, 2 to the second, 8 is 2 cubed, 16 is 2 to the fourth. So the denominators of these fractions are powers of 2. And this is the first term here, this is the second term here, this is the third term, and this is the fourth term. So the n that I want to use matches the power of 2 that I want in the denominator. So this is going to need to be a 2 to the n in the bottom. Now notice the relationship between the numerator and the denominator in all 4 of these fractions. The numerator number is exactly 1 less than the denominator number. So an easy way to do that is to just take that denominator, which we know is 2 to the n, and subtract 1 from it. So that way that numerator will always be 1 less than whatever the bottom is. So here's our formula for a sub n. And then this next one here is actually powers of x on top. This first one is like an x to the 0, then x to the first, then x to the second. But remember, this is kind of like our first term, our second term, our third term, our fourth term, and so forth. So the power on the x this time is actually 1 less than the number of the term that we want. So for the third term, I actually want to use a power of 2, for example. So the power of x that I want should be 1 less than the n that I'm plugging in. So this needs to be an x to the n minus 1. In the bottom, this is something that you need to be on the lookout for. You'll start to get more experience with these as you do a lot of these, but these numbers in the bottom are actually factorials. 2 is 2 times 1, or 2 factorial. 6 is 3 factorial, 3 times 2 times 1. 24 is 4 times 3 times 2 times 1, or 4 factorial. And 120 is 5 factorial. This denominator is implied to be a 1, which is like a 1 factorial. And this denominator is like a 0 factorial, which is also defined to be 1. So what we want in the bottom is a factorial, but again, the type of factorial we want is 1 less than the n that we're using. For here I want 2 factorial even though it was n equal to 3. So it's just like the power. We used a power of n minus 1 on the power of x. We want an n minus 1 factorial in the bottom so that the power on the x matches the type of factorial that we use in the bottom. So there's our nth term formula. And when we talk about sequences, we often want to know whether or not they converge or diverge. So to figure that out, we're going to just take the limit as n goes to infinity or x goes to infinity, depending on what kind of notation you're looking at, and see what happens as the number of the term gets bigger and bigger and bigger. If that converges to a value, then we say the sequence converges. If the sequence goes to infinity as the terms get bigger and bigger and bigger, then we say that the sequence diverges. If the limit as we go to infinity is dne for any other reason, then no conclusion can be drawn concerning the sequence without further investigation. So for example, if I want to know whether or not the sequence a sub n equals to n squared over 2 to the n minus 1 converges or not, then what we would do is we would look at its limit as n goes to infinity. Now initially when I plug in infinity, I'm going to get infinity squared, or infinity on top, and 2 to the infinity is also infinite. So this would technically be a dne limit because infinity over infinity doesn't have a value, but it's not necessarily going to be a sequence that diverges unless we explore this a little bit more. So if we investigate it, we'll notice that this is one of those indeterminate forms that we can use with L'Hopital's rule. L'Hopital's rule says if you have anything of the form infinity over infinity or 0 over 0, then what you can do to find the limit is to take the derivative of the numerator, which in this problem would become 2n, and take the derivative of the denominator. And the derivative of 2 to the n is 2 to the n back again times ln of 2. You get that extra little change of base in there because the base is a 2 instead of an e. Now if we plug in infinity, 2 times infinity is still infinity, and 2 to the infinity is still infinity. So it's still in that indeterminate form. But the nice thing about L'Hopital's rule is that you can keep applying it. So now if we take the derivative of this numerator, derivative of 2n is 2, and the derivative of 2 to the n is 2 to the n back again times ln of 2, but we already had one of those there, so there's now going to be 2 of them left. So now if we plug in infinity, the numerator is fixed at 2, and 2 to the infinity is infinite. So this is now 2 over something really, really big, which is going to go to 0. So this is actually a sequence that would converge to 0. Okay? Now just as a little review's sake, suppose that we have sequences that look like x to the n. Now if the absolute value of x is less than 1, which implies that x is a fraction, then this would be something like the limit as n goes to infinity of, say, 1/2 to the n. What we're saying here is that that's going to go to 0. And you can see that because that denominator is going to be bigger, and it's going to go to infinity when we raise it to that power, and that's going to go to 0. So anytime you have a fraction raised to something that's getting really, really big, then that limit's going to go to 0. If your base inside here, this x, is actually something less than or equal to -1, like -2 or -3, for example, so say we wanted the limit of -3 to the n, then that's going to be dne, because if n is even, then this will be a positive value, and if n is odd, then this will be a negative value. So this is dne because it's going to oscillate between positive and negative values, so it's not going to converge. What happens if your base is 1? Well, then the limit as n goes to infinity of 1 to the n is just going to equal to 1. your sequence will be 1, comma 1, comma 1, comma 1, and so forth for every term. So obviously that's going to converge to 1. And finally, if your base is greater than 1, so for example, say I wanted the limit of 2 to the n, or 3 to the n, or 4 to the n, obviously that's going to blow up as n gets really, really big. So this is going to be infinity, or diverge, if that base is greater than 1. So if it's a fraction, the limit is 0. If it's negative, the limit is d and e. If the base is 1, then the limit is 1. And if the base is bigger than 1, then it's infinite. Now, the next thing we want to do is write the first 5 terms of each of the following sequences. You can also draw a graph for these if you want to help you visualize what's going on. And then we're going to determine the convergence or divergence of each. If it is convergent, we want to find the limit. So to find the first terms of these, what I often encourage students to do is to either use the table feature on your calculator, or you can even use lists on your calculator. Both options work. So all you would have to do is go to your y equals, if you're going to use the table command, and you would just type into y sub 1 the formula for your nth term. And we're using x's here instead of n. So this would be 1 over x to the 3 halves. And usually, since we want the first 5 terms, we're going to want to set our table to start at 1, and we want our change in table to go up by 1s. And then if we hit table, not graph, but that's what the graph would look like. You can see that that's going closer and closer to 0 as x gets really, really big. But in terms of the table, this would be your first 5, 6, 7 terms. So when n is 1, we get 1. When n is 2, we get 0.35355. When n is 3, we get 0.19245, and so forth. And you can see that as you progress down this table, these y values are getting smaller and smaller. So that's further evidence that this probably does converge to 0. Okay, so all you would have to do is maybe make a little table here for each of your first 5 values, and then you would just write down the corresponding nth term that we got in our table. So I'll just write down what we got. 0.5355 was the second term, 0.19245, 0.125, and 0.08944. Now that's going to be your first 5 terms. To find out if it converges or not, you just look at your limit. And it's going to be the limit as n goes to infinity. So we're going to look to see what this nth term is doing. And obviously here, as n gets really, really big in the bottom, this is going to act like 1 over infinity, which we know goes to 0. So in fact, this does converge, and it does converge to 0. Okay? So on the next example, we would do exactly the same thing. You can either use your table command or your list feature on your calculator. It's up to you. You can graph it if you like, and then we're going to find those first 5 values. So if we pull up the calculator, we're just going to go back to that y equals, and we're going to clear this out and type in our next function, which in this problem is going to be the square root of x divided by parentheses square root of x plus 1. And if I just go to table, there's our first 5 terms. So as we can see from our table and our y values here, as the n gets larger, these y values are actually getting slightly bigger each time. And you can keep on going down and arrowing down if you want, and you'll start to see that they are getting bigger, but they're getting bigger fairly slowly. So let's investigate whether or not this sequence converges or not. So to see if it converges, we're going to take a look at the limit as n goes to infinity of the square root of n over the square root of n plus 1. Initially, when we plug in infinity, the square root of infinity stays infinite, and the square root of infinity plus 1 will be infinite. So this is one of those indeterminate forms, but we can apply L'Hopital's rule here. So this would be the limit as n goes to infinity of the derivative of the square root of n, which if you think of that as n to the 1/2, this is going to be 1/2 n to the negative 1/2. And on the bottom, same thing, 1/2 n to the negative 1/2, and the plus 1 goes to 0. So these actually are the same, which means everything's going to cancel out, and we're just going to get 1. So in fact, this does converge because we got a finite value, and it converges to 1. And so that's why those y values in that table were getting slowly bigger and bigger, but they're not going to get bigger than 1. Okay, if we try ln of n squared over n, and we want to find the first 5 values of that, then again we can pull up our calculator. And we're going to go to our y equals, clear this out, and we're going to type in the ln of n or x squared divided by our x. And I'm going to set my table back to start at 1 again because I remember moving it. And then we're going to go back to our table. And here's our first 5 terms: 0, 0.69, 0.73, 0.69, 0.64, 0.59. So the first few terms here, we actually see some going up and down. It starts to go up, 0.69 and then 0.73, and then it goes down to 0.69 at 4, and then down to 64, 0.59, 0.55. And if you continue down after that first few terms, after the third term, all of these terms start to continue to decrease. And that happens sometimes with these sequences where there might be a few terms initially at the beginning, a finite number of terms at the beginning, where the sequence might initially increase, and then it turns around and decreases, or vice versa. And that's okay, as long as eventually, as n gets really, really large, you start to approach a single value. Okay, so we have our first 5 terms. Again, I'm not going to copy those down, but you can see them right here on the screen. Oops, I went too far. And so those would be your first 5 terms, and now to see whether or not this converges, we're going to take a look at that limit. So the limit as n goes to infinity of the ln of n squared over n. Initially, infinity squared stays infinite, and the ln of something infinite stays infinite. And then obviously the bottom is going to be infinity as well. So it's one of those indeterminate forms. So if we apply L'Hopital's rule, you can take the derivative of this, and a couple of things to keep in mind here. You can use properties of logs and think of ln of n squared, bring down that 2 and think of it as 2 ln of n, and then take the derivative of that instead, which would be just 2 times the derivative of ln of n, which is 1 over n. Or if you did the derivative of ln of n squared immediately from this form, you would do 1 over n squared times the derivative of n squared on top, which would be 2n. So you'd get 2n over n squared, which reduces to 2 over n. So no matter how you do it, you're going to get a 2 times a 1 over n on top, and then the derivative of n on the bottom just goes to 1. So this is acting like a 2 on top and an n on the bottom, and as n goes to infinity, this is going to be like 2 over something infinite, which we know goes to 0. So this converges to 0. Okay, so just remember for this one, those first few terms kind of increased, and then after that third term, all the terms continued to decrease, so that eventually it was converging to 0. For number 13 here, we've got a sub n equals n minus 2 factorial over n factorial. So we can go ahead and go to our calculator and make a table of values here. What I would possibly recommend as an option, if you want to use that factorial button, you can certainly do that, but we have done a few examples already where we see that some cancellation can go on here. So what you might keep in mind is that this is really the same as n minus 2 factorial, and then n factorial, which is actually bigger than n minus 2 factorial, would be n times n minus 1 times n minus 2 factorial. So these would cancel. So this is really like 1 over n times n minus 1. And that's a simpler formula to deal with, and it's actually going to be the form we want to use when we take that limit. So if we go and we take the limit of this as n goes to infinity, you can see right away that that denominator is going to be infinity times infinity, or just infinity, and it's 1 on top, so this is going to go to 0. So we know right away that this is going to converge to 0. And to see those first 5 terms, we can use the calculator again. So if we go to our y equals, you have your option of just doing 1 divided by parentheses x parentheses x minus 1. That would be the more simplified way probably of typing it in. And then if you go to your table set, let's start it at 1. Then here's your first 5 terms. Now it's not defined at 1 because that would make your denominator 0. And then at 2 you're at 0.5, and then at 3 we are at 0.1667, 4.08, and then all these terms start to decrease from there, and that's where we're going to get that convergence to 0. Now just as a refresher in case you forgot, if you wanted to use that factorial button, you would have to go to the math key, and then you can arrow either to the right or backwards to the left to that PRB, which is probability, and option number 4 there is where the factorial command is. So if you ever needed to know that, that's where you would find it. Okay, so if we take a look at the next example, here our nth term is 1 plus negative 1 to the n. So let's write out these first 5 terms, and we don't need a calculator for this one because this one is easy enough to do in our heads. So if n is 1, you'd have an odd power, so this is going to be 1 plus negative 1, which is just 0. If n is 2, now this is an even power, so this becomes a positive 1. 1 plus 1 would be 2. If n is 3, we're back to an odd, so this is back to negative. 1 minus 1 will be 0. If n is even, we're back to positive, so this will be 2. And if n is 5, we're back to odd, so this is going to be negative, and this is 0. So based on this, you can see that this sequence is going to oscillate between 0 and 2, 0 and 2, 0 and 2. So is it going to converge? No, because we're not converging to a single value. We're divergent because we're oscillating between 2 distinct values. How about this sequence right here, sine of 2 pi n? Well, on this one again, we could probably do this by hand. If we let our n be 1, then this is sine of 2 pi, which is 0. If n is 2, that's sine of 2 pi times 2, or sine of 4 pi, which is still 0. If n is 3, sine of 6 pi is 0. If n is 4, sine of 8 pi is 0. And if n is 5, then we're at sine of 10 pi, which is 0. These are all multiples of 2 pi, and we know that sine is always 0 at any multiple of 2 pi. So there would be your first 5 terms. Does it converge? Obviously, right? It's every term is 0, so it's convergent to 0. Okay, how about cosine of 2 pi n? So what if we have a cosine function here? So now if we let n be 1, then cosine of 2 pi we know is 1. If n is 2, cosine of 2 pi times 2 is cosine of 4 pi, that's 1. If n is 3, we're at cosine of 6 pi, which is 1. So now all of these are multiples of 2 pi, but for cosine, cosine is always 1 at every multiple of 2 pi. So this is also convergent, but this time it converges to 1 because we're using that cosine function instead. How about if we use cosine of pi n? So now if n is 1, we have cosine of pi, which is negative 1. If n is 2, cosine of 2 pi is 1. If n is 3, cosine of 3 pi is the same as cosine of pi, which is negative 1. Cosine of 4 pi is 1. Cosine of 5 pi is back to negative 1. So does this sequence converge? No, it diverges because you're oscillating between 2 values. So on these next two, what we want to try to do is use the squeeze theorem, if possible, to determine the convergence or divergence of the sequence. So here we want to know whether or not cosine of n over n converges or diverges. So one thing we could try with this squeeze theorem, especially useful with trig functions, is that we know that cosine of n, since it's a cosine function, is always bounded between negative 1 and 1. It oscillates between negative 1 and 1. So that gives us an inequality, a boundary here that we can use to help us with the squeeze theorem. So we know that cosine of n is between -1 and 1. Now if we divide everything through here by n, which we can do since we're only going to be using positive n's, so that won't flip any of our inequalities around, then this relationship is still true as well. So we know that cosine of n over n is bounded between -1 over n and +1 over n. So what the squeeze theorem lets us do is it says if you know that you have a relationship like this with these inequalities, then the limits of each of these has to satisfy that inequality as well. So if I take the limit as n goes to infinity of the left, the middle, and the right, then these limits have to satisfy this inequality as well. And we know that the limit of 1 over n as n gets really, really big goes to 0. And likewise, the limit of -1 over something really, really big goes to 0. So if the limit of cosine of n over n is bounded between these two, then the only place it has to go is 0 as well. So by the squeeze theorem, we can say that this implies that the limit as n goes to infinity of cosine of n over n must be squeezed in between these, so it has to go to 0 as well, which means that the sequence converges to 0. Okay? Now let's try something similar for this one. If we have the sequence n times sine of 1 over n, if we try to pull the squeeze theorem on this one, we would start with that sine of 1 over n. That's a sine function. No matter what the angle is, we know that sine of any angle is always squeezed in between -1 and +1. So now, since n is a positive number, because remember your n's are always positive integers, if I multiply all three of these inequalities by n, then this would become n times sine of 1 over n, and n. So this inequality is still true as well. So now let's try our squeeze theorem on this. So if I take the limit as n goes to infinity of the left, the middle, and the right, what are we going to get? Well, the limit of minus n as n goes to infinity, that's negative infinity. And the limit of positive n as n goes to infinity is positive infinity. So what the squeeze theorem tells us is that this limit that we're looking for in the middle is squeezed in between negative infinity and positive infinity. Well, that doesn't tell us a whole lot, right? That doesn't really tell us anything. It could be anything in between negative infinity or positive infinity. So here the squeeze theorem doesn't really help us at all. It doesn't tell us any bounded value that we know we have to approach. So let's try a different alternative. If we want to know whether or not this limit converges, let's take a look at that limit directly. Initially, the n out front here is going to infinity. 1 over n is going to, 1 over infinity is going to 0, and sine of 0 is 0. So this is going to an infinity times a 0, which is one of these indeterminate forms that we've talked about in the past, but it's not one of the indeterminate forms we can use for L'Hopital's rule. We need to make it either be 0 over 0 or infinity over infinity. So to turn this into one of those two fractions, I'm going to take this n and I'm going to flip it down to the denominator. So let's turn this into the limit as n goes to infinity of sine of 1 over n over n to the -1, which is the same as 1 over n. So all I did is I took n and I turned it into 1 over 1 over n. Now if n goes to infinity, 1 over infinity is 0, and sine of 0 is 0. And in the bottom, 1 over infinity is 0. So this is acting like one of our legitimate forms that we can use L'Hopital's rule for. So let's apply L'Hopital's rule. The derivative of sine would be cosine of 1 over n times, using the chain rule, the derivative of 1 over n would be negative 1 over n squared. And the derivative of the 1 over n in the bottom is also going to be negative 1 over n squared. So these two things cancel each other out. So what we're looking at here is the limit as n goes to infinity of just cosine of 1 over n. 1 over infinity goes to 0, so this part goes to 0, and the cosine of 0 is 1. So this limit does exist, and it equals to 1, so this converges to 1. You might recall vaguely from Calc 1 that we did have a formula. This is like the limit of sine of theta over theta as theta goes to 0, and we had defined that to be equal to 1. So it's that same limit, we just proved it using L'Hopital's rule. Now when we talk about sequences, sometimes we talk about whether or not they are monotonic. Now monotonic means that the terms are either non-decreasing or non-increasing. So non-decreasing basically means that each of your terms is less than or equal to the term before it. So a sub 1 is the same as or smaller than a sub 2. A sub 2 is the same as or smaller than a sub 3. A sub 3 is the same as or smaller than a sub 4. So either your terms are staying the same or they're slowly getting bigger here, okay? Non-increasing would be the same idea but going in the other direction, getting smaller. So here your a sub 1 would be greater than or equal to a sub 2. A sub 2 would be greater than or equal to a sub 3, which is greater than or equal to a sub 4. So your terms are getting smaller if you're non-increasing. Now to determine whether a sequence is increasing, decreasing, or neither, we're just going to look at some of those terms. So if we have a sub n equals 3 plus negative 1 to the n, let's make a list here, a table of some of these terms. If n is 1, that's odd, so we'll be using a negative here. 3 plus negative 1 would be 2. If n is 2, that's even, so this becomes positive. 3 plus 1 would be 4. If n is 3, we're back to an odd, so this is negative. 3 minus 1 is 2. Even, we're back to plus, so this becomes 4. And hopefully you can see here that these are going to alternate between 2 and 4 and 2 and 4 and 2 and 4. So are these terms getting bigger or smaller consecutively? No, they're oscillating back and forth. So this would be neither increasing nor decreasing. Okay? Now if we look at ln of n over n, we can do something similar here and look at a chart, and you can do that on your calculator. So if I pull it up and I go to my y equals and I just type in ln of x divided by x, and I'm going to start my table at 1, and if we look at some of these terms, you can see that I start at 0, then I go up to 0.346, then I go up again to 0.366, and then I go down to 0.346, and then down to 0.32, then down to 0.29, then down to 0.27. And if I continue down, all of these now are going to continue to get smaller and smaller. But initially, those first few terms increased. So I increased from 1 to 2, and then from 2 to 3, and then after 3 I decreased. Okay? So that would be one way to look at this. So in my chart at 1, this was 0, at 2, 0.34657, at 3, 0.3662. So these are increasing initially. But then after 3, all the terms start to go down again. So we're back to 0.346557, and then 5 is 0.32189, and so forth. Okay? So then after, we decrease. Another way to kind of consider whether or not a sequence is increasing or decreasing is to do it through calculus. And to tell whether or not something increases or decreases means to look at its derivative and see if that derivative is positive or negative. So if we try that here, let's think of this as the function ln of x over x. Then the derivative of that using the quotient rule would be the bottom x times the derivative of the top, which is 1 over x. So that's low d high minus high d low, the top, times the derivative of the bottom is 1 over the bottom squared. And this reduces to x times 1 over x is just 1 minus ln of x over x squared. Now that denominator is always positive because it's squared. So if we want to know whether or not this is increasing or decreasing, we need to know when is this going to be 0. And that's going to happen when that numerator is 0. And when does ln of x equal to 1? Well, that happens when x is e, which is approximately 2.7 and so forth. So if we get larger than e, then this is going to become negative because you'll get ln of 3, ln of 4, ln of 5, which are bigger than 1. So when x is greater than or equal to 3, this derivative becomes negative, which means it decreases. Okay? If we're before 3, then we're going to increase. And that's exactly what we saw here. So after 3, after n equals to 3, this sequence decreases. Okay? Now let's think about that same idea using this next example. You can certainly look at a table, and that's fine, and list some of your values here as proof that this increases or decreases, or we could use a little bit of calculus as well. So to determine whether or not this increases or decreases, let's think of it as the function 2x over x plus 1. Then the derivative of that, using the quotient rule again, would be low d high, so the bottom times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. And when you simplify that top, you're going to get 2x plus 2 minus 2x over x plus 1 quantity squared. And those two x's cancel out. So this is positive 2 over x plus 1 squared, which is always positive. So this is always greater than or equal to 0 for all x. So that means the original function f, which in this case is our sequence, is always increasing. So without even looking at some terms here, I know that these terms are always going to be increasing based on the derivative. And we can't really do that for this next example because we don't have derivative rules for functions that look like this. We don't have a derivative rule for a factorial, and we don't have a derivative rule for something like this in the top that doesn't really have a formula per se. So in this case, we'd have to actually plug in some different values of n. And you can't even really type this into your calculator into your y equals. You would have to, physically plug in 1. So when n is 1, 2 times 1 would be 2, 2 minus 1 would be 1. So this numerator is just going to be a 1 on top. And on the bottom, 2 to the first is 2, and 1 factorial is 1. So this is going to be the same as 1/2, which is 0.5. Now if you let n be 2, 2 times 2 is 4, 4 minus 1 is 3. So we're going to do the product of 1 and 3. So this top is kind of like a factorial, but you're only multiplying the odd numbers. You're leaving out the evens. And we're going up instead of down. So when n is 2, we're going to do the 1 times the 3. And on the bottom, we would get 2 squared times 2 factorial. So this is going to be 3 over 4 times 4, which is 16, and that's 0.375. I'll do one more here. If n is 3, then you'd be doing the 1, the 3, and the 5 on top, and you'd get a 2 cubed, which is an 8, times a 3 factorial, which is a 6. So that's going to be a 48 in the bottom and a 15 in the top. So as a fraction, or excuse me, as a decimal, 15/48 is going to be 0.375. 3125. And I'll do one more here. If n is 4, then we would do 1 times 3 times 5 times 7 over 2 to the 4th times 4 factorial. So that's going to be 15 times 7 on top, and 2 to the 4th is 16, and 4 factorial is 24. So as a decimal, that's approximately 0.2734. So this one is a little tedious. You'd have to do it by hand, but as you can see here, all of these values are getting smaller and smaller. The power of 2's and the factorials in the bottom are going to become much bigger than the number that you end up with on the top. So this is decreasing. Okay, what if we have n factorial over 2 to the n? To show that this one is either increasing or decreasing, again, you can't use calculus because we don't have a derivative rule for factorials. So here you would have to use your calculator to show this. So let's go ahead and make a table of values here using n factorial over 2 to the n. So I'm going to type in x, and then remember the factorial button is under math. You have to arrow over to probability, and it's option number 4. And then we're going to divide that by 2 to the x. So if I look at my table of values, I've got 0.5 to 0.5. Now that's not increasing or decreasing, that's staying the same. And then I go from 0.5 to 0.75, so I'm getting bigger. 0.75 to 1.5, that's getting bigger. 1.5 to 3.75, it's getting bigger. So this is what we call monotonically increasing. Their terms are either getting bigger each time or staying the same. So I'm going to copy a few of these down, but I want you to notice that as n gets larger, these y values get really big really fast. Okay, they're getting up into the millions after only 14 terms. So what that's showing us and proving to us is that this numerator is going to get bigger faster than the denominator can. It's going to get bigger at a faster rate than the denominator. That's why this is going to grow so quickly. So in our chart, you got 0.5 for 1, and then 0.5 again for 2, so that's when it was staying the same, and then 0.75, and then 1.5, and then 3.75, 11.25, 39. So these are getting very big very fast. And what that's showing us is that, first of all, this is monotonically increasing. That word monotonic basically just means your terms either stay the same like they did here, or they get bigger each time. So these were definitely getting bigger. And what this is showing us is that this numerator must be growing at a faster rate than the denominator, because the fraction as a whole continues to get larger. If the denominator was getting bigger faster than the numerator, then this whole fraction as a whole would be going to 0. The fact that this is getting bigger and blowing up to infinity is showing us that this does not converge. So here the limit, as n goes to infinity, of n factorial over 2 to the n must be going to infinity, since you can see from the terms that they're getting so large. So this is showing us that factorials grow faster than exponential functions do. And that's a fact that you can kind of memorize and use in future problems. Now we have a theorem that says that if you have a sequence a sub n that's bounded and monotonic, then it converges. Okay, so we know what monotonic means. That means it's either staying the same or increasing, or staying the same or decreasing. If it's bounded, that means that you're either bounded from above or from below. So if you're bounded from above, what that implies is that all of your terms in your sequence are less than or equal to some upper bound for every a sub n. So every term has to be smaller than or equal to this upper bound. If you're bounded from below, then all of your terms in your sequence have to be greater than or equal to some lower bound for every a sub n. So if you think of your terms as having sort of this upper bound, if you're monotonically increasing, you're either staying the same or getting bigger, but if you're bounded from above, you can't get any bigger than that u. So if you're monotonically increasing and you have an upper bound, then that means you're going to have to converge to that upper bound u. In the other direction, if you're monotonically decreasing and getting smaller or staying the same, and you're bounded from below by this lower bound L, then you can't go any lower than L because you're bounded, but if you keep decreasing and getting closer to that L, then you must converge to it. So this gives us a way of determining whether or not a sequence converges if we don't have any other techniques to figure out whether or not it converges or diverges. So for example, suppose that we want to show that the sequence 3 to the n over n factorial converges. Now we can't do this in the way that we've done in the past. Normally what we like to do to show something converges is we take its limit as n goes to infinity. And on this one, 3 to the infinity is infinity, and infinity factorial is infinity. So it looks like a good candidate for L'Hopital's rule, but the problem is we don't have a derivative rule for a factorial. So I can't take the derivative of that denominator to use L'Hopital's rule here. So I need some other strategy. Now think about what 3 to the n means. 3 to the n means 3 times 3 times 3 times 3 times 3 and so forth n times. Now think about what n factorial means. That means n times n minus 1 times n minus 2 and so forth. If we do it from, instead of going from n down to 1 and we go from 1 up to n, that would be like 1 times 2 times 3 times 4 times 5 times 6 and so on, all the way up to n. So what you can see here is that if I look at this, what I'm going to notice on top is that eventually the numbers on the top are always 3's, but the numbers on the bottom are getting bigger and bigger and bigger. So eventually the numbers on the end of this scale are going to get much bigger than the 3's on top. So your instinct should probably be that this factorial on the bottom is going to get faster, bigger, faster than that numerator, because that n, as it gets larger and larger, is going to give us a much bigger product down here than just a product of the same amount of 3's. So that's kind of the idea here. Now if we actually look on our calculator, we'll see some boundedness. So let's first take a look at our calculator and let's type in our actual sequence. So 3 raised to the x divided by x factorial. And if we look at our table, you'll see that initially in this sequence the first term is 3, then it goes up to 4.5, then it stays the same at 4.5, and then after that n equals 3, these terms go down, 3.3, 2.0, 1.0, 0.4, and that's going to continue to be the case as I go bigger and bigger n's. So what this shows us, just by looking at the terms themselves, is that after n equals to 3, this sequence is monotonically decreasing. Actually, after n equals to 2, it's monotonically decreasing. So we know that this is a decreasing sequence after that very first initial term. Now the next thing I want to show you on the calculator is I want to compare the size of 3 to the n to the size of n factorial. So let's go back to our y1, and this time I'm just going to type in 3 to the x in y1, and then in y2 I'm going to type in x factorial. And if we go to our table, This first column are these 3 to the n. So these are your numerators, and the second column over here are your denominators, your factorials. So what you'll notice is that the 3 to the first is bigger than 1 factorial. 3 to the second is bigger than 2 factorial. 3 to the third is bigger than 3 factorial, and so forth. But when does that change? When does the factorial become bigger than the power of 3? Right here when n is 7. When that happens, your denominator is now bigger than your numerator. And if we scroll down here, you'll see that after 7, those denominators get much bigger than that numerator does. And that's what's going to show us that we have a bound here. Okay? So after n equals to 7, 7 and greater, that denominator, that factorial, is bigger than 3 to the n. So let's formalize this. So first of all, we know from our chart that when n was 1, we had 3. When n was 2, we had 4.5. When n was 3, we had 4.5. When n was 4, we had 3.375. When n was 5, it was like 2.025, and then 1.0125, and so forth. So what this showed us was that we were decreasing. And we could even say monotonically decreasing after n equals to 2. Now what we also noticed by comparing the size of 3 to the n and n factorial is that when we looked at n's that were greater than or equal to 7, we saw that 3 to the n was less than or equal to n factorial. The numerator was smaller than the denominator. And all of these were positive, so they're bounded from below by 0, obviously. So what we can do is we can divide through, since all of these are positive values, let's divide everything by n factorial. Now 0 divided by n factorial stays 0. If I take 3 to the n and divide by n factorial, then we get that in the middle. And n factorial divided by n factorial is just 1. So what this shows us is that 3 to the n over n factorial is bounded from below by 0 and above by 1. And since we're decreasing and we're bounded from below by 0, then by that theorem that we just talked about, if you are monotonically decreasing and bounded, so we are decreasing and bounded from below by 0, then we must converge. And in this case, since we're bounded from below by 0, then we must converge to 0. And so what this is showing us again is since this is converging to 0, we're saying that this limit is 0. That's showing us again, that's further proof that factorials grow faster than exponentials. And in general, you can say that the limit as n goes to infinity of any base k raised to a power n compared to n factorial, that limit's always going to be 0. So no matter what base you pick, whether it's 3 to the n, 4 to the n, 5 to the n, eventually that n factorial is going to be bigger than that exponential function. Okay? So factorials are pretty fast acting, and they're pretty, they grow really, really fast. Okay? Now the last one here is comparing a polynomial, in this case a quadratic, n squared, to an exponential 2 to the n. So what we want to look at here is what's happening to this. So if we pull up our calculator again, I'm going to type this in and look at a few of our terms. So I'm just going to go to y equals, clear these out, and I'm going to type in x squared divided by 2 to the n. I just want to see whether or not this sequence converges or, increases or decreases. So I'm going to start at 1, and just get a look at a few of these terms. So we start at 0.5, then we go up to 1, up again to 1.1, then down to 1, then down to 0.78, down to 0.56, down to 0.38, and then from there they continue to get smaller. So again, initially the first few terms we increase, but then from 3 on we decrease. Okay, so you can ignore those first few finite terms where we don't decrease, because eventually n is going to go to infinity, and that's really what we're looking at, is that long-term behavior. So the first few don't really matter, but eventually this does continue to decrease. So we know that we have a decreasing sequence. So this decreases, and if we want to know whether or not it converges, we would initially want to try and find this limit. Now we couldn't find this limit directly in the last example because we had a factorial, and so L'Hopital's rule wouldn't work since we didn't have a derivative rule for factorials. Here we do have derivative rules for n squared and derivative rules for 2 to the n. So if initially this is infinity squared, which is infinity, over 2 to the infinity, which is infinity, this fits L'Hopital's rule. So we can take the derivative of the top and the bottom, and the derivative of n squared is just 2n. The derivative of 2 to the n is 2 to the n back again times ln of 2. If I plug in infinity now, 2 times infinity stays infinity, and 2 to the infinity is going to be infinity as well. So it's still that indeterminate form, so let's apply L'Hopital's rule again. The derivative of 2n is just 2. The derivative of 2 to the n is 2 to the n back again, times ln of 2, times the ln of 2 we already had. So the top stays fixed at 2, and the bottom becomes 2 to the infinity, which is infinite, and 2 over something big goes to 0. So this converges to 0. We didn't have to bother trying to find upper and lower bounds because we were able to use L'Hopital's rule to actually get this limit. So what this is showing us is, since this sequence is converging to 0, that means that the denominator must be growing faster than the numerator so that the fraction as a whole is going to 0, because the bottom is blowing up towards infinity faster than the top does. So that means this exponential function in the bottom is growing faster than that quadratic in the top. And that's true in general for any kind of polynomial. In general, exponentials will grow faster than polynomials of any degree. So if you had an n to the k over 2 to the n, whatever that power k was on that polynomial, eventually you could find an n large enough so that the denominator would be bigger than that numerator. So in general, exponentials grow faster than polynomials, but factorials grow faster than exponentials. Alright, that concludes our video lecture on sequences. Good luck.